Yeah, so this is a condensed version of the talk we just gave at NeurIPS on the biggest advances in computer vision in 2024. We to decide what the most important papers were, we looked at a huge amount of research that came out in 2024 and decided to split it into different themes. So I have two themes, and Peter has more. Uh, Two themes that I want to talk about are this interesting trend this year of transforming powerful image-based models into video equivalents, and then a trend we're seeing on DETRs, uh, which is a specific type of object detection model taking off and exceeding YOLOs. Um, so specifically with respect to the two themes I talked about, I'm going to be talking about SORA um, and SAM2. SORA takes this beautiful video image-based diffusion pipeline and extends it to video generation. And SAM2 takes the tool that we all know and love, where we hover over an image and it can take masks out and extend that to running on videos. And then I'm going to talk about three specific papers that introduce various improvements to the DETR framework that allow them to have excellent performance. So to set some context for the SORA conversation, we it's important to mention where we were in terms of video generation at the end of 2023. So the existing framework was based on the MAG-VIT, which is a an attempt to extend the VQGAN framework to uh, video compression. I'm not going to spend much time talking about the specifics of the VQGAN architecture, but essentially it's just an autoencoder that attempts to output a discretized latent code. The VQ, the MAG-VIT v2 has this incredible thing where it actually outperforms state-of-the-art video compression tools on um, bit rate versus human preference. So we actually get better video compression than something like H.265. So we get this discretized latent code, then we pass it through an autoregressive transformer, and we get these short, not super detailed, but still clearly making progress on video generation videos. Then just 4 months later, uh, we get this. This, in my mind, is a stepwise improvement. This is SORA. Um, Notice how the video is a minute long. It's it's 1080p, so it's very high resolution. It's got a lot of different people moving in it. This the reflection of light in puddles reminding me of the RTX demos for high-end video games. Um, Absolutely stunning. Absolutely stunning. There's still some issues where for example, if you look in the background, you can see some issues with some of the way the people are walking, and here her hairstyle actually changes after it gets out of frame for long enough. These issues in my mind are similar to the issues that we see in diffusion models, where sometimes the person will have like six fingers. You basically just have to be looking for them. Um, so I'm going to talk about SORA. Caveat: SORA does not have an actual paper. So I'm basically going to fill in some gaps from its technical report based on replication efforts and concurrent research. Um, so the first step, we have uh, we have a large language model watch a lot of videos and write very detailed captions for them. There aren't a lot of good video data sets. So a lot of these research efforts spend the first amount of time generating a very high quality data set, and a standard step here is just to have an LLM label everything. Um, there are other steps that are important in that process. One of them is that they actually filter these data sets by aesthetic scores, and also like make sure that the videos have lots of motion, so you don't just end up generating like static videos. But yeah, you have like GPT-4 watch a huge number of videos. Then we take the take the video and then embed it into latent patches in a similar way to MagVIT v2, except that it's using a variational autoencoder framework instead of a VQ GAN. Um, Variational autoencoder attempts to output latents that look like they're sampled from a Gaussian distribution, as opposed to latents that are discretized. This is very important because diffusion likes to sample continuous spaces. Getting a diffusion sample from discretized spaces is challenging. So replication efforts actually use the MagVIT v2 framework. We don't really know what SORA itself is using, but it's probably something similar. And they seem to get a lot of benefit from the fact that you're doing both spatial and temporal compression, because videos are extremely redundant between frames. So it makes sense to want to use the temporal information to get better understanding of the frames. So this the third phase, after the second step, is to just pass this all through a giant diffusion transformer. So the importance of that is diffusion transformers are shown to scale super well as you add more data to that, as you add more compute. I think it's interesting to note that the MagVIT v2 uses an autoregressive transformer to sample from this discretized latent space, whereas the SORA uses a diffusion transformer to sample from this continuous latent space. Transformers for the win. Another interesting thing to note, once again, we don't know exactly what SORA is doing, but a lot of the concurrent works actually replace the standard DDPM diffusion model. DDPM stands for denoising diffusion probabilistic model method. I don't remember what the M stands for. This is the way that we've done diffusion for years, and recently people have started to shift to a rectified flow, which is a different parameterization of a similar type of idea. It seems to give much better results for these types of things. So likely they're using something similar to rectified flow. The open source reproductions and related works tend to use that. And finally, the last step is, you guessed it, throw a huge amount of compute at it. I couldn't figure out how to get this video to loop, so I'm just going to play it manually a couple times. So this is with the base amount of compute. This is with 4 times the compute. And this is 32 times the compute. The difference is so stunning. It's so clear. And the beautiful thing is that the diffusion transformer, the original paper that introduced that concept, actually showed just it didn't really matter what the hyperparameters for the transformer were. Just as you throw more compute at it, it gets better. Just linear, log linear correlation. The more compute, better. And we see that here. They don't tell us anything about the hyperparameters that they're using for the diffusion transformer. They just say, yeah, more compute, better. Which is, I think, pretty neat. The replication efforts try to do that as well, but they run out of budget. So you go into open source and their discussion, they're like, yeah, this is how long we trained it. And we trained it for that because we didn't have any more money. These are extremely expensive models, and OpenAI did an excellent job. So yeah, my favorite my favorite thing that came out in 2024 is just SORA extending the per frame diffusion model to video generation. And it's generally available as of last week. It was generally available 2 days before we gave our talk, which is kind of fun. So the next thing I want to talk about is SAM. I'm realizing I'm running a little over time, so I'm going to move a little faster. On the Roboflow platform, SAM has saved 75 years of labeling time by automatically generating these masks. We're the biggest hosted API for SAM. SAM also allows you to take a model that was trained to generate boxes and generate masks, which significantly decreases the amount of compute effort that goes into training the backbone model. A huge number of our users are actually running these detection models on per frame on a video. SAM2 extends this idea of promptable mask generation to video object segmentation. So in one frame, you get a box, and then you know where the object is, pixel by pixel, in all the other frames of the video. So here's a example of that. You provide a prompt for a couple cells, and it just keeps track of them with the masks. It's sick. So brief high level overview of what's happening here. We provide a prompt. It can be points, can be a mask, can be a box, and it fills in the rest of the object throughout the video. The structure of the network looks very similar to the original SAM, except that there's a memory block where um, basically the network is allowed to look at the representation that it has extracted for the past few frames. Um, and then to build the data set, they also use the SAM paradigm where you actually use the model in the loop to label your data. So you have labelers going and labeling stuff, and simultaneously they're training the model. And as the model gets better, they allow the labelers to rely on the model more and more. And it significantly reduces the time to create a massive video data set. As we mentioned before, video data sets are hard to come by, so this was a huge advancement. Um, so great extension of the the SAM framework to video, and we're happy to be expanding our usage at Roboflow. Next thing I want to talk about is how DETRs are creating a new frontier for real-time object detection. DETR stands for a detection transformer. So once again, transformers doing interesting things. Um, so maybe this is a little negative towards Ultralytics, but you see, we see that the past couple YOLO versions haven't really given much of a benefit to their accuracy versus their throughput. It's worth noting that this is a map 50 through 95, whereas on Roboflow we typically report map 50. So these numbers are lower than you might be used to seeing, but this is how research communities tend to do it. So yeah, 9, 8, 10, 11, not much of a change. 7. So arguably they've hit a bit of a plateau. This latency is worth mentioning explicitly. This is a tensor RT, so very optimized framework for running these models. So DETRs have not shown the same behavior. Just in 2024, we've seen models coming out that are significantly expanding the frontier of what we thought was possible with real-time models. So Define, newest model, actually hits almost 59 AP at a similar latency, whereas the YOLOs are at 55. So a nice like +4 AP improvement with similar latency. And all this has just come from the last year. So we're going to talk a little bit about like what these DETRs actually did that made such a difference. So RT DETR actually showed that you can match the speed of a YOLO with a DETR. This was like DETRs tend to be historically on the high performance but low speed regime. So they've been sitting on the top of the SORA leaderboard for Coco for years, as long as you allow unlimited compute. But now RT DETR showed that actually you can reformulate the model head and get a significant speed up. And then you can DETRs do not require NMS, non-maximal suppression. Whereas if you actually include the time that NMS takes in your benchmark of a YOLO, then in fact this sped up DETR outspeeds the YOLOs that existed at the time, so up to YOLO V8. Super interesting, because at this extreme low latency regime, the NMS actually takes the longest amount of time versus the model. Then LW DETR suggests that the YOLO models don't tend to benefit that much from pre-training. In a lot of other areas of computer vision, pre-training is extremely important to get high performance. And LW DETR just spends a lot of time asking why that's true and attempting to show that DETRs benefit more from pre-training. So here they mention this really, really interesting thesis that the reason YOLOs don't benefit that much from pre-training is because they take a long time to converge. So early in training, you see a big gap between the model that was pre-trained and the one that was not. And late in training, as the model is starting to converge, that gap doesn't really exist anymore. The DETRs, on the other hand, converge within 60 epochs. So they're able to maintain that performance gap. Um, Super important stuff. And similarly, LW DETR, because it benefits more from pre-training, shows superior transfer to tasks that maybe have smaller data sets, so they don't have as much data to train on in the first place. So we like that they used our RF100 benchmark. We think that's a very important benchmark, and they show state of the art results on RF100. So finally, yeah, the define. I didn't include this in the slide because it's very technical. But define just introduces a bunch of bells and whistles to improve performance, and we end up with a plus 4.6 for the same latency. So we're very interested in models that work better with less data, and we're excited to see that DETRs are kind of emerging as a new Pareto frontier in that space. And what we're excited to see next, we would like DETRs work now both in the extreme low latency regime and the high latency regime. We would like a single model family that expands from low to high latency. These real-time ones aren't testing with bigger backbones. We also want to pre-train the models more and see if it increases the transfer performance even more. And then we want more people to be benchmarking in RF100 because we think Cocoa is maybe a little saturated, and B, not super relevant to y'all. So that's the end of my section. Peter, would you like me to maintain the slides, or would you like to take over?
I'll share my screen.
Cool.
Okay. Yeah, so sort of building off of the themes that Isaac has been exploring, which is like um, sort of this idea of pre-training, which to be clear is like training a model on some big data set where it learns a lot about a lot, and then your your fine-tuning step would be taking that model and transferring it to a much smaller, like more specific data set where it learns how to like kind of take those ideas from the big data set and kind of use them in a fine-grained manner. Um, so I guess the big theme of 2024 for me is how do we get these big foundation models that know a lot about a lot for vision, the same way that we've been seeing for text, right? So I'm sure most people here have interacted with ChatGPT and know that, this model, like, it's not perfect. Maybe it doesn't have good reasoning abilities, but it sure knows like a lot about a lot. And if you can query it about facts very easily, right? Um, so why don't we have the same thing for vision? And so to start off, I'd like to, these are the papers I'll be referencing, but yeah, I'd like to prove that these models that exist, like ChatGPT, actually don't know a lot visually. So I start with the sort of the theme, why can't LLMs see, right? So this is an image of showing a watch to ChatGPT. If you ask it what time is on the watch, it says it's approximately 10:10, which is completely wrong. Um, and you can say like, okay, so maybe it's not seeing the image in high enough resolution, but even if you zoom in to the watch face, it still can't see the time, right? And you could say, okay, well, maybe the model doesn't know how to read watches, but you can see if you actually just describe it visually. I didn't say which was the minute hand or the hour hand. I just described it visually. Then it's able to accurately read the time. So it's not able to generate this description from that image, because if it was, then certainly it would be able to reason of what time it is, right? Um, and so one thing I think is funny is that if you see it kept saying that the watch was at time 10:10. I also asked it to imagine a watch and tell me what time it was in a separate context, and it said the time was 10:10. And then if you go and look, most pictures of watches on the internet are like, trying to sell watches, and most of the product images of watches have the time 1010 as their like display. So clearly the model is sort of like doesn't know how to see. It actually is just like kind of remembering that the captions for most of these images say the time is 1010. And same thing happens with Claude, although it doesn't, maybe it learns a little bit better because it imagines some weird random time instead of the time that it's memorized. Okay, so the question is, why can't these LLMs see these fine-grained details, right? And so I think one of the coolest research this year is this new data set called MMVP, which is trying to answer this question and sort of also prove that they can't find these fine-grained details in the image, right? So, for instance, it asks, "Is the school bus parked facing away from the camera or facing the camera?" And it gets the answer wrong and then makes up an explanation, right? So the question is why. Um, and so they actually are able to generate like quite a long list of images where the model like can't see these fine-grained vision details, and they do it using sort of an interesting method, which is they find pairs of images that have very close similarity using clip as a measurement of the similarity of the model, and then very far similarity using this model called Dino. So clip was a model that was trained contrastively, which means that it got like it got 25 images in, and then those images came with captions, and it jumbled up the images and the captions, and it tried to learn how to predict to match which caption to which image, right? But you could sort of see the problem here is that a lot of these captions you don't actually need to look that in depth into the image to figure out which caption would go to this image, right? If I'm looking for you know if one caption is image of a horse and the other caption is like New York City, like I don't have to spend very long looking at the image at all to determine which caption goes to which. And I don't need to find, where are the windows on the buildings or where are the hoofs of the horse. So that sort of does it basically encourages the model not to find these fine-grained visual features, right? DynaV2 is a model that has been trained only from visual data, and it's been trained like to sort of like reconstruct patches of the image. So it knows a lot more about sort of like the fine-grained visual features of the images. So by finding images that are very different from Clip and from Dino, or very similar according to Clip and very different according to Dino, they're able to construct pairs of images where the model gets questions about these images wrong when you ask it about fine-grained visual details. So you can see like all the big language models here, they all just say the same answer for both for each image. How many eyes can you see on the animal? Because to them, the input image looks exactly the same. And that's the problem, right? So on this data set, humans do like 95% accuracy, whereas like the next best is like 40%. It's a huge drop off, right? And so basically they sort of try to kind of solve this problem by weaving in Dino features with Clip features, but it doesn't really work too well. And so that kind of leads us to the big research that's happening in 2024, which is like, okay, how do we solve this problem and get like language models or just big foundation models in general to like look at fine-grained visual details? So Florence 2, which is available on Roboflow, you can fine-tune, run inference, use it in workflows. Is a really cool model that tries to solve this problem. And so you can see what they do is they train this like large language model on a variety of tasks ranging from what they call spatial hierarchy, which is like, is it looking at the whole image or looking at very small details in the image, and semantic granularity, which is like, are you just saying there's a car on the road, or are you going to like describe like all the relationships of the concepts of the objects on the scene, right? Like the car is driving on the road and it's next to the woman and yada yada. And sort of like diving deep linguistically. So if you construct their thesis, if you construct a data set that has a range of all these types of tasks on both axes, then you'll get a model that can reason or like understand high level things about the world while also understanding like fine-grained visual things, which we don't have a model that does both yet, really. And this is sort of how the data set is constructed using 3 levels of annotations, either text describing the whole image, text describing little regions of the image, or text describing little regions of the image that's also referring to like a phrase in a paragraph. And what they show is if you train a model using that data, and then you take that and you sort of only take the visual part of the model and you try to train an object detector using that, it works really well. And using that data set instead of like ImageNet, which is one of the most popular image pre-training data sets, your model trains 4 times faster and it gets to 7 points higher. So yeah, another model that we're really excited about that's also available for fine-tuning on Roboflow is PaliGemma 2. And yeah, you can fine-tune and run inference using Roboflow using this model. So data looks pretty similar. It doesn't quite have like the full range of like tasks on the visual hierarchy and semantic granularity. Mostly it's been trained to do object detection, segmentation. It does visual question answering as well. So it's got yeah, it's got a lot of linguistic capabilities. Oh, to be clear, it's using the Gemma 2 language model, which is like Google's really good distillation of Gemini. It's a really good small language model. But yeah, for instance, the small size here is 2 billion, whereas for Florence 2, it's 0.2 billion. So this one has a lot more sort of like knowledge and reasoning capabilities. But yeah, so if you transfer learn this model to Coco, so this isn't kind of taking the vision encoder and slapping an object detector on it. It's actually using the whole model. So trying to predict objects like using text tokens. So it gets worse by a significant amount than doing an object detector sort of traditionally, but it's pretty like this is a very good result for using a language model to find objects in an image, which is 43.6 map at the highest resolution and the highest model size. And their MMVP result, at least for PaliGemma 1, was SOTA. And they didn't report it on PaliGemma 2, which is sad because I bet it'd be better. But yeah, to be clear, MMVP is that data set of images that look the same to clip but far to dyno. So it's really cool by training a model to make sure it looks at fine-grained visual features. It actually does like learn how to distinguish if two images of an eagle have one eye or two eyes present in the image. And then the last big model that we're really interested in is AMB2, which sort of is kind of trying to train a foundation model like CLIP that was trained contrastively, but trying to make sure that it can learn fine-grained visual details while doing that training. And so the cool thing about AMB2 is it's self-supervised, so it doesn't have a bunch of labels. You can train it on like internet scale data, right? And so the way that they do that is they kind of train. So again, they scrape a bunch of images with captions off the internet, but instead of trying to do the contrastive matching from image to caption, what they do is they try to predict the caption using a language model. But they also try to predict the image, which is the interesting idea from this paper. So they break up the image to a bunch of patches, and then they feed it like 7 patches in a row, and then they try to have you predict the 8th patch, like literally like reconstruct the pixels. And by doing that, it's able to learn a lot of fine-grained visual details about the image. You need to know, exactly where this tree is to predict how to complete that little tree shape, right? So they collect a ton of data. This is Apple, and they use sort of the same data set that they use to train their state-of-the-art clip-based model. So they collect a ton of high-quality clip data. And what you see is that your model continues to improve using bigger models and higher resolution. So like it's notable that it improves with higher resolution because that means it's like looking at more of the fine-grained details. And it's notable that it improves when using a bigger model because that means that it's actually kind of becoming like a big foundation model like ChatGPT, but for images. And so we're really interested in this, especially from the perspective of object detection. So here's their results, taking the model and training it, transferring it to Coco, and they get 60.2, which is, for context, like the smallest YOLO V8 is like 37 map or something on Coco, and the largest is like 52 or 53. So this is, blowing that out of the water. And yeah, so used by doing this strategy of learning fine-grained visual features on a ton of data, hopefully we have a smarter model that can use less, that we can use as a backbone for an object detector maybe, or kind of in some way have transfer its knowledge to previously unseen data and require fewer examples to do so because it knows more about the world already.